Today we're going to talk about real-world examples of sine and cosine. Um, these examples are called simple harmonic motion. Anything that moves in a periodic nature, it gives you examples here like oscillations of a pendulum swinging back and forth. They're high to low to high to low. Or the orbit of a satellite, away and back, or vibrations of a tuning fork. And that could be vibrations of anything that makes sound, like a guitar string vibrates. Um, so those are some examples. Some other things, anything that moves in that same motion, like if you had a rock on your tire and your tire is spinning and it comes back down to the pavement. So the rock's on the pavement, it goes around, comes back down, up and down, up and down. That would also be simple harmonic motion. And so we can write all of these kinds of equations using sine and cosine. So our first example here is talking about the depth of water off of a pier in Port Aransas. So the water at the pier rises and falls. And so what it's talking about is, here's my pier, and here's my little pylons down below. And the water depth is coming up on those pylons and then going back down, up and down, up and down. And so the depth of the water changes according to high tide, low tide. So here's what that looks like over time. We have a high point, a low point, another high point. And it says this graph is talking about the depth of water beginning at noon on March 19th. So this is noon on March 19th. So that's my 0. And then it says that T is hours after noon. So this is 1 hour afternoon. So 1 p.m., 2 p.m., 3, 4, 5, etc. This would be midnight. This would be 1 a.m., 2 a.m. And then Y represents the depth of the water in meters. So this is the height in meters, and out here is our time in hours. All right. So we have some questions that are just designed to familiarize us with the graph. So it says, at what time and date is the first high tide? Well, our first high point is right there at the beginning. So our first high tide is at noon on March 19th. Now the second high tide is out here at 14. But 14 is, like we said, this is midnight, this is 1 a.m., 2 a.m., so this is 2 a.m. the next day, March 20th. The first low tide, right here, that looks like that's at 7, so this would be 7 p.m. on March 19th. So that's kind of the way the graph is designed. So next it says, how long does it take the tide to complete one cycle? That means to go from its high point to its high point. So that would be the distance in between these points, which is 14 hours. So 14 hours, that's going to be our period. The period of this graph is 14 hours. All right, then they ask us to write an equation in terms of sine and another one in terms of cosine. So this is the same thing that we did with our problems where we were given the graph. So it's just this one has an application attached to it. So we need, in order to do this, our A value, our amplitude. So our amplitude is the height off of the midline, which in this case it looks like we're going up 3 or down 3. So our amplitude is 3. We need our B value, which is 2 pi divided by the period. And we said the period is 14 hours. So that's pi sevenths. And then we need the equation of the midline. So for the midline, it's just the x-axis. So there is no vertical shift. For the horizontal shift, that's going to depend on whether we're writing the equation for sine or whether we're writing the equation for cosine. So if I'm writing the equation for sine, I'm looking for the first time I cross the x-axis, which is right here at 3.5. For the cosine, I'm looking for the first high point, which happens to be right there on the y-axis, so there's no shift. Okay, so we're ready to write our equations. We have all of our information. So the sine equation, we're going to have y equals, and our amplitude is 3, but I want you to notice here on this graph from 3, on this graph, we're going down first. And so if we're going down first, you know the sine graph normally goes up first and then down. If we came out here and we went up first, we could write this as a positive sine graph. Because we're going down first, this is going to have to be a negative graph, a negative sine graph, -3 to reflect it, sine of our b value, pi/7, our left-right shift, so minus 3.5, and there is no up-down shift. For cosine, it's going to be positive because we're starting high, so +3 cosine of pi/7, and there's no left, right, or up-down shift. So both of those would give us the exact same graph. One of them is just sine and one of them is cosine. So next they are asking us questions about our graph, and it says, what is the depth of the tide at midnight on March 19th? And if you look up here, midnight on March 19th would be right here. So we kind of have that marked off, and it looks like it's about 2 meters. But we don't want an approximation, we want an exact value. That's why we have these equations, because we can put these equations in the calculator and find out exactly the depth at midnight on March 19th. Now, midnight, we just said, is when x is 12. So we're going to type one of these in there, and then we'll look and see what's going on when x is 12. Now, I'm going to use the second one. It's shorter, a little bit easier to type in, but I also want to talk about a few things when we're typing in the calculator. So let's take a look. So for this one, I have my 3 cosine, and you notice that when you hit the cosine key, it automatically opens a parentheses. Well, that creates a little bit of a problem for us, because if we were going to have a left-right shift, we need another set of parentheses inside there. So because it opens up and we can't change that, go ahead and put your pi/7, but then open a new set of parentheses for your left-right shift, then close them both out, and then if we have an up-down shift, it would go on the outside of that. All right, so there's also a couple of other things other than just typing that we need to check on our calculator. So you need to go to your mode key right here. Make sure you're in radian mode. And then in order for our graph to look exactly like the one on my paper, I need to set my window to be exactly like this paper. So I'm going to go to the window key, and I'm going to set this from 0 to 15. That's what's on the x-axis here. So 0 to 15. And then my y-axis, -4 to +4. So that's what I type in here, -4 to +4. And then when we hit graph, it should graph exactly what's on our paper, so that it looks the same. Okay? So check all of those things. Be sure that when you type your equation in the calculator, put an extra set of parentheses for your left-right shift. Be sure you're radian mode, and check your window so that you match your paper so that it will look the same. Okay, so now we're ready to answer our question about what's happening when x is 12. Well, there's a couple of places we could look, but the easiest one, once we've got it all in here, is just to go to second trace and calculate the value when x equals, and just type in 12. Hit enter, we get 1.870. And remember that that's a y value, so it's in meters. All right, then it says, at what time is the depth of the tide 1 meter? Well, this is a y value. Y equals 1 meter. Well, to put y values in this calculator, we have to go to y equals. So I'm going to go to y2 and put in 1. I'm going to hit my graph key. And then we can see that there's a couple of answers here. So we're just going to go with the first time when y is 1. Usually on your homework paper, I think it will tell you first time or second time, but here we're just going to go with this first one. So I'm going to second calculate the intersection, number 5, hit enter, enter, enter. Oh, it went to the second one. I want the first one. So second calculate the intersection, hit enter, and then I'm going to slide over closer to the one I do want to find. Then hit enter, enter. So y is 1 when x is 2.7427. So 743. Now, if we want to figure out exactly what time that is, because x is representing hours after noon on March 19th. Well, we know that 2 hours after noon would be 2 p.m. And this is 0.75 approximately of an hour, so that's going to be about 45 minutes. But if this is something that's a little hard for you to figure out, if it's not quite as exact as 0.75, here's what you can do. You can take whatever this decimal portion is, so in this case 0.743, and multiply that times 60 minutes. So we get 44.58 minutes, or approximately 45 minutes. So this is 2 hours and 45 minutes after noon, or at 2:45 p.m. on March 19th. So to convert this back to time, just multiply your decimal times 60. Okay, in our next example, it says that we have a weight that is at rest hanging from a spring. So this line across here represents like a table or something, and this spring is attached to it below the table, and this little weight is attached to the other part of the spring, the other end of the spring. So we know that if we were to pull down on this spring or push up on the spring, it's going to start bouncing. So that's what they're talking about when they say the weight is oscillating up and down. It's pulled down 6 centimeters. So they're going to pull it down first, 6 centimeters, centimeters, and then they're going to let go. And when they let go, it's going to bounce back up the same amount that you pulled it down, up and down, up and down. And for the first few times, it will be exactly, well, really close to 6 centimeters. 6 down, 6 up, 6 down, 6 up. Now, after after a period of time, of course, it's going to slow down a little bit because gravity is also going to have an impact on this. But for the first few rotations, for the first few oscillations up and down, it will be very close to 6 centimeters in both directions. So they want us to make a sketch of that on our axis. So the first thing that we did was pull it down. We pulled down 6 centimeters. So we're going to start down here at -6 centimeters and let this x-axis be at rest. Like if it weren't moving at all, that's where it would be, and we pulled down on it first. So it's going to start down here. Now it's going to bounce up and down, so it's going to go up to 6 centimeters. And it says that it completes a cycle every 3 seconds. So I'm going to go out here 1, 2, 3. And I know if it started down, then in 3 seconds, it has to end down as well. 1, 2, 3 seconds. All right, so halfway in between here, which is going to be at 1.5, it should be at its high point, because we've talked about this with all of our graphs. They always have the same intervals in between every motion. And so, let me move that down. It doesn't look quite even. Okay, so our graph comes up and comes back down, and it would do that over and over and over again. Now, if you want to find out exactly where it crosses, you could. This is 1.5, so half of between 0 and 1.5, we could find that, but it's not necessary to find that. All we need to do is find our high and our low, and we're going to be able to write our equation. So again, first question is just to familiarize us with the graph, make sure we understand what we've sketched here. And so each axis, the x-axis is representing time in seconds. 3 seconds is how long it took to complete the cycle. The y-axis is representing the position of our weight. Either above or below rest. Above rest or below rest. So it's going above and below, above and below. All right. So it wants us to write an equation for this curve. Well, to write an equation, we need our amplitude. Our amplitude is how high or low it's going away from our midline, which in this case is 6. We need our b value, which is 2 pi divided by the period. Well, between points here we have 3 seconds, so that's going to be the period of the graph. So divide by 3. So our b value is 2 pi thirds. And then if we're going to write this as, we get to choose. It didn't say to write it as a sine or a cosine in particular, but if it starts out low, then it would be easiest to write this as a cosine equation with no shift. But also recognize that this is going to have to be a negative cosine because we started low. So it has been reflected. But there's no shift up or down or left or right if we use cosine. So we have y equals, and then our amplitude, but we have to be negative because it's reflected, -6 cosine of 2 pi thirds x. All right, so we're going to type that into our calculator and see if we can get our calculator to graph what we have on our paper. All right, so here's our equation, -6 cosine of 2 pi thirds. Open a new set of parentheses just in case there's a left-right shift. Put in your x. And then check your mode. You want to be in radians. Go to your window and set it up like your paper. So this one went from 0 to 3 seconds on the x, and from -6 to 6 on the y. And then hit graph, and we should get what's on our paper. Okay. So let's look at our questions down below. It says determine the position of the weight at 1.5 seconds. Well, at 1.5 seconds, we are right here. And I think we probably could answer that question without the calculator because that's going to be our high point. That one is going to be 6 centimeters above rest. I don't think we need a calculator for that, but we could put it in. At 1.5, that would be an x value. So we could go second calculate the value when x is 1.5, and we get our 6. Okay. Next, it says use the graph to find the time when y is 3.5 for the first time. So again, to put y values in, we have to go to y equals. We're going to y2 and putting it 3.5. We're going to graph it, and it wants us to find the intersection for the first time, this one. Oh, sorry, can't see it. this one. So second, calculate the intersection. Move over there closer to that point. And it says that we get x is 1.047. Now, 1.047 is an x value, so that's in seconds. And if it's a positive 3.5, when y is positive 3.5, 3.5 was up in here somewhere, so that would be a position of our weight above rest. Position or height above rest. If it had been a negative 3.5, it would be below rest. All right, so those are just two examples. So what you're going to do in your homework is try to make a sketch of our graph and using our sketch, and really you only need one cycle just like we had here. And then you should be able to find all of the information you need to write an equation. Since these are real world applications, you should be able to use your equation to answer questions about your graph.